Are you seeing my screen?
Yeah, perfect.
You hear me good? Awesome. All right, let's do this. Well, thank you so much for the introduction, and thank you for inviting me to give this seminar today. Thank you to the whole Department of Mathematics and the SIAM and IMA student chapters. I really appreciate it. And I was telling Adam yesterday that I feel like a bit of a celebrity. This is my first time giving a talk to a audience overseas from America. So thank you for having me, and I look forward to this. So yeah, my talk is about the mathematics of the Maya civilization, but you'll see I've also folded in a lot of information about some other civilizations and their mathematics as well. So for those of you who don't know, over here in America, on this past Monday, we usually celebrate what's used to be known as Columbus Day, the discovery of America by Christopher Columbus. I should put discovery in quotes because we know he did no such thing. And so recently it started to become rebranded as Indigenous Peoples Day to instead recognize the indigenous people of the Americas who were affected by colonialism and the contact between Europeans and the Americans. So, one thing that I wanted to do was sort of highlight the mathematics and the traditions of one such American ancient civilization, that being the Maya. So, hopefully you learned something new from this. And yeah, I'd love to take questions at the end on anything I present here. But before I get into the meat of the talk, I want to make a few disclaimers that I think you should know about me. First is I am not an expert on the Maya civilization. I'm just someone who's very fascinated by it. I'm definitely not an expert on the history of mathematics. I am not a history expert. My background is solely within mathematics. And I'll just go ahead and might as well say that I'm not an expert since I'm making all these disclaimers. There might be some questions that I won't be able to answer since I'm not, a professional in the subject. I'm more of like an amateur who just finds the subject really interesting. But hopefully you do as well. So I wanted to start by just doing a brief introduction to numeral systems in general, just to put the Maya numeral system into context before I present it. And the first question I have is a warm-up. I'm a math teacher, so I love to give my audience members and students warm-up things to think about. And the question I have for you to think about is, if you had to, how would you define the number 3, right? You all have an idea of what 3 means in your mind, but if you had to speak to someone who'd never seen the number 3, what would you tell them? How would you define 3 to someone who had never heard of the concept before? And this is an interesting question because this is the task that, people have when they're teaching little kids about numbers, right? My guess is that if you're trying to define the number 3, you're probably thinking of some physical representation of the number 3, or you're trying to define it in relation to other numbers, such as 1 or 2. And those are all perfectly valid attempts, but when trying to define the number 3, it's probably easier to think about what's not the number 3. So the following things are not the number 3. This is not the number 3. None of these 3 words are the number 3. This Roman numeral here is not the number 3. This sum is not the number 3. This symbol that you might think to do with your hands is not the number 3. And last but not least, this High School Musical trilogy does not capture the number 3. And the reason is that 3 is found in all of these bullet points, right? They're all representations of what I would call 3-ness, but actually capturing a definition for the number 3 is quite difficult. And, the logicians or set theorists among you will have a formal definition of what 3 means, but in colloquial talk, all we can really do is represent numbers. And so that's the whole point of a numeral system, is to represent quantities in visual form using some predefined set of symbols. And obviously there are many ways to do this. So I would say that at the very least, a numeral system should have a symbol or a string of symbols that can be assigned to each whole number, or I say in parentheses a sufficiently large subset of whole numbers, because when you think about it, there are infinitely many whole numbers you will never encounter or use or say or think about in your entire lives, right? There's a finite subset of numbers that humanity will ever use, and so we don't really need to represent infinitely many numbers in practice, but a sufficiently large subset would do, right? But whatever symbol we use has to be unique to the number. So there are really two conditions here, right? Every whole number in your set should have some symbol that represents it, but no symbol should represent more than one whole number. Otherwise, that symbol becomes ambiguous. However, it's totally possible for a number to have multiple representations. For example, if we're looking at real numbers, we can represent 3 as 3.0, 2.9 with a bar over it, which is 2.999 repeating, and this is all perfectly valid, right? But that's just the minimum requirements. An ideal numeral system, in my mind, should have a couple additional requirements. For example, I feel like the symbols that we use in our numeral system should be intuitive and easy to remember, meaning there should be as few symbols as possible, and each symbol should somehow be closely connected to the number they represent abstractly, right? So it's easy to remember. The symbols should be easy to read or write or display, since we do have to communicate what the meaning of the symbol. So in particular, it should be visually distinguishable from other symbols in the system. There should be a method for expressing large quantities and conveying the magnitude of a number quickly, so that at a glance we can see how large a quantity is. And of course, we like to do arithmetic, algebra, calculus, right? Mathematics. So it should allow for the quick and efficient doing of math, right? So these are just some qualities I think an ideal system should have. And what I'd like to do is now explore a couple of numeral systems that I'm sure you've heard of and sort of rate them on this sort of scale here. So let's start with the tally mark system. Very ancient numeral system. I also call it the official numeral system of keeping score and keeping track of days in prison, as the picture here suggests. And tally marks are incredibly old. One of the first recordings of tally marks were on this Ishango bone, which was found in the Democratic Republic of the Congo, about a century, I think, or so ago. And you can see here on the bone, there's these notches here that historians believe are tally marks, one of the first recorded uses of tally marks. And this bone is roughly 20,000 years old, but tally marks probably extend back quite a ways further. And if you really think about tally marks, there are only really two symbols that the tally mark system uses. There's a symbol for 1, a single stick, and a symbol for 5. 4 sticks with a cross through it, right? And between these two numbers, all we need to then know is how do we go from one number to the next? How do we count? And there's really only 2 rules to counting and tally if you think about it. The first is that if you ever see 4 sticks appear and you want to count to the next number, replace it with the symbol for 5. But otherwise, you're just going to draw a stick next to whatever the last symbol was that appeared. So this is what we call an additive system, right? To get from one number to the next, you just sort of concatenate another symbol onto the existing symbols, right? And that's how you get the next number. And it's remarkably efficient. It can represent literally every whole number this way. Unfortunately, there's no symbol for 0, however, so kind of a bummer. So when I think about the tally mark system and how it would rate on the 4 ideal qualities I want in a numeral system, in terms of easy to remember and intuitive, I would give it a perfect 10, honestly, because, what's easier than writing tally marks, right? Tiny kids can learn how to write numbers in tally marks. Is it easy to read and write? I would say it's pretty easy to write and pretty easy to read and interpret it. So I might give it a 9, but I might dock at 1 point because honestly, it's sometimes hard to see if you have 4 tally marks versus 3 tally marks. So I'll actually knock it back to 8. And case in point, you probably didn't even notice that I made a change on my slide by taking away a tally mark because 3 and 4 are kind of hard to distinguish at a glance sometimes. And that theme will come up again a bit later on. How easy is it to express large numbers? I would say incredibly difficult, right? I mean, imagine trying to express Jeff Bezos's annual salary in tally marks. You'd be writing tally marks for the rest of your life and still not capture it all. So I would say it earns a 0 for this category. And in fact, there is no number for 0 in tally marks, which is why it's just a blank space right now. And is it easy to do arithmetic? I would give it a 2. Tally marks were not meant for arithmetic. They're meant for counting, right? Particularly days in prison. So I would give it a solid 2 in that category. So if I average these 4 ratings, tally mark system from me gets a rating of 5. So not terrible, but also not great either. Kind of failing marks, if you will, 5 out of 10. So next are the Roman numerals system you've probably all heard of. I call it the official numeral system of old buildings, grandfather clocks, and essay outlines. As you can see here from these three examples. And this top one here is actually a building in New York, city where I'm from, New Amsterdam, which is what it used to be called. And this is the year it was founded. So let's explore Roman numerals a bit more in depth, right? So it's also a pretty ancient symbol, not as ancient as tally marks, but about 3,000 years old, give or take. And here we've upgraded. Instead of 2, there are 7 main symbols now, most of which you're probably familiar with. And you can see, just like tally marks, they also thought it was important to have a symbol for 1 and 5. They just thought they should have a few others, which will make it slightly easier to express larger numbers, right? They had a few other symbols that were rarely used, like the ones I'm describing here below, but really the 7 main ones were what comprise their numbers. And again, you can represent really every whole number, but there is no symbol for 0, which is, again, a bummer. Here I included the algorithm for how to count up in Roman numerals because I wanted to compare it particularly to tally marks that really only had 2 rules for counting. Here, the Roman numeral system has at least 9 rules. If you ever thought about why it's so hard to count, this is kind of why. There's a lot of things you have to check at the end of your Roman numeral to decide how to count up from it. So the more important thing is, how do we read Roman numerals, right? So we read them from left to right in an additive way, like tally marks. But if a smaller symbol appears before a larger one, then it's subtractive in that pair of symbols, which is where things get confusing. So looking at a few examples here, if we did some conversion practice, if I took this Roman numeral, which is me just concatenating the 7 major symbols, M through I, then all of these symbols are in decreasing order, or rather I should say non-increasing order, which means I should just take their sum in an additive way and what they represent, and I get 1666, aka the year that Isaac Newton was born. Maybe it's a coincidence, maybe not, who knows. Then if I take the Roman numeral that was on the New Amsterdam picture in New York City from before, all I've done is swap the L here with an X. So this is still in non-increasing order, so I still read the symbols additively, and that gives me 1626. Then if I were to swap 2 of the letters in this last Roman numeral, like swap the C and the D, swap the V and the I, now we have 2 pairs that are in increasing order. D is larger than C, V is larger than I. So for those pairs of symbols, I read them subtractively. So I have 500 minus 100, and the end I'd have 5 minus 1, but everything else would be additive. That's why Roman numerals are weird. And if I did this, I'd get 1424 instead. 2 more examples. If I took this really long string of Roman numerals, you can see there's only 1 increasing pair from C to M, which means that's the only pair that will get read subtractively. Everything else is additive. And if I add them up, I get 1988, aka the year yours truly was born. And lastly, if I take this final example, MMCDC, XLXX, IVI, there are 3 pairs of increasing numerals, C to D, X to L, I to V right here. So those would be 3 pairs that are read subtractively, and then I'd add up everything else, and I'd get 2565. But there's a trick here, because this last Roman numeral, if you are looking really closely at it, you might be able to see that it's not a legal Roman numeral. The 9 rules for counting on the previous slide cannot ever give you this string of symbols. But that'd be hard to see at a glance, right? Whereas in other numeral systems, it's really easy to see if you've written a legal or illegal number. This is a major flaw with Roman numerals, I think. Not to mention the fact that representing something like 1988 takes like 9 or 10 symbols, right? So how do I rank this system? Easy to remember, intuitive. I would give it about a 7. You know, it's not as intuitive as tally marks, but you know, still pretty intuitive. Is it easy to read and write? I would say absolutely not. I give it a 4 in that category. It's very hard to determine if a Roman numeral is legal or not. Easy to express large numbers. I give it a 5. It's a bit easier than tally marks. You've got some symbols for higher order numbers, but otherwise it still takes a long time to get to the thousands. And easy to do arithmetic, I would give that as well a 4. It wasn't meant for arithmetic and algebra, right? That's not the main use of the Roman numeral system. So in averaging these, ironically enough, I still get an average rating of 5. So funny enough, I rate this system about as well as the tally mark system, which is why we don't really do mathematics in either of these systems. But let's get to the main event, right? Hindu Arabic numerals, aka the official numeral system of planet Earth. Why do I say that? Well, if you look at this Babel notice, which is what these notices are sometimes called, maybe you have them in the UK as well, I'm not sure, then you'll see that they're translated in a bunch of different languages that use a whole host of diverse symbols and characters. And yet, what do they all have in common? In the highlighted section, they all use the same numerals, which I think is particularly strange, right? Why should there be thousands of languages, but yet they all refer to phone numbers using the same string of digits, right? And that continues with a bunch of other languages, including Arabic, which has a very different script. So how did this come to be? Well, we call them Hindu Arabic numerals because they extend from Hindu civilizations from about year 700 AD, but they were formulated over many centuries and they were revised constantly. One thing that they introduced that other systems didn't was the idea of zero, introduced by Brahmagupta in 628 in his humbly titled book, The Correctly Established Doctrine of Brahma, which I always think is a hilarious title. But it was a revolution, right? Zero was not really known to the Western world at this time. And then it took a Persian mathematician, Al-Khwarizmi, where we get the word algorithm from, if you're curious, when he wrote a treatise on the Hindu numerals when he was studying in India. So he brought this back to the Middle East, and it became very popular there for a while. Here on the left, you can see the evolution of the Hindu Arabic numerals from what they used to be to what they've sort of evolved into. And what really sort of sparked the popularity of the system is really a guy you've probably heard of, Leonardo da Pisa, aka Fibonacci. And he wrote this book, Liber Abaci, the book of calculation. Abaci is sort of like abacus, right? And he called this Indian method the modus Indirum, method of the Indians, when he studied in North Africa. And he said this quote, "From a marvelous instruction in the art of the 9 Indian figures, the introduction and knowledge of the art pleased me so much above all else." So Fibonacci was really moved by this new numeral system, and especially its use of the number 0, and thought, I want to try to write a book and spread this throughout Europe, which he did through the help of Gutenberg and the printing press in like the 1500s, and the rest from there is history, right? The European trade and colonialism spread the number system throughout the world. Fascinating to think about the fact that the Europeans particularly went back to India and colonized it for a while. So I always think how weird it would be to be, part of India and you created this numeral system, and then centuries later someone comes back and brings you like a new version of it, and you're like, wait, what? We created this. So that's how it spread. And what makes it a different system is that it's a base 10 system. It's a place value system. Here I present again the algorithm for counting, not because I don't think you can count numbers, but rather just to see the algorithm that is required really in your mind when you're counting to the next number in Arabic numerals. And you can see it's really like a sort of 5-step process, which introduces the idea of ordering our digits, ordering our symbols, so that we can tell how to get to the next one, right? So because it's a base 10 system, we can express our numbers in this format where you have the base raised to different powers, and then the coefficients are just the digits of your number, right? D0 through Dn. But usually we just concatenate the digits. An example is shown here, right? When we write the number 2826799, well, we're really saying a long mathematical expression based on powers of 10, right? So this is what makes this different from tally marks and Roman numerals, which are not place value systems, right? Each digit place does not hold a particular power of 10 or any other power. So how do I rate this system? Our homegrown, I shouldn't say homegrown, but our system that we use every day to do math. Well, I would give it a 9 in terms of easy to remember. It's got more symbols than either tally marks or Roman numerals, but there are only 10 symbols, and certainly we can remember 10 symbols, right? However, I do knock it down a peg because those symbols aren't really connected directly to the number they represent, right? Easy to read and write, I would say also a 9. Each symbol is pretty straightforward to write. But again, having to read them all could be a bit challenging if it's a large number, because then you have to insert commas or points to indicate orders of magnitude. Otherwise, you're just looking at a long string of digits. I give it a 9 in this category for the exact same reason. And easy to do arithmetic and algebra, I would say it gets a 9 here as well. And you'll see for reasons later on why I dock it a point in this category. But I average these, and obviously this is a rating of a 9. So much improvement over the last two, but I think that there's something lacking, which, again, I'll explain as I go through our next numeral system, the system of the day, the Maya numeral system. So before I talk about the intricacies of the system, just a brief summary of the civilization called Maya. So they lived in southeastern Mexico and Central America, roughly 4,000 years ago, in fact, so a pretty ancient civilization as well. And they lived really much up until the year 1697. However, they're still descendants of the Mayas living in these territories. People like to say that the Maya are extinct, and the existing Maya would probably take offense with that. There are lots of descendants of the Maya still living in Mexico and Central America today. And you've probably heard they've made numerous achievements in science, math, architecture, such as this pyramid here, very famous in southern Mexico. They spoke close to 30 languages, and they too had a numeral for 0 long before most of the rest of the world even thought to give 0 an actual symbol. So that was a really remarkable achievement. They also, you probably heard about their astronomy and their calendar. They calculated the length of a solar year to be accurate to 4 decimal places, which is pretty incredible given that this was thousands of years ago, and our modern value has not really improved much on it with the advent of GPS and modern science. And what makes it even more miraculous is that they have no recorded evidence of ever doing multiplication, much less using fractions or decimals or real numbers or any modern techniques of mathematics. So you might wonder, how do they calculate a solar year to 4 decimal places when they didn't have decimal points and they didn't know what decimal meant? It's a great question. Maybe I'll address it later. But the point is that we know about the Maya numeral system largely from this book here. This is a page from the book called the Dresden Codex, and it's actually the oldest surviving book that was ever found in the America continents. So if you just zero in on one page of this, you can see what looks like quantities, right? What looks like a way of counting things if you look closely. And we're going to return to this page from the Dresden Codex, but hopefully by the end of our talk, we can actually understand what all these symbols mean. So to start, what makes the Mayan numeral system so awesome is it's also a place value system, right? It was a place value system before most of the world was using place value systems, except they use a base 20 or vigesimal system. So they represented numbers as multiples of powers of 20 instead of 10. So if we were doing this with Hindu Arabic numerals, we only have 10 symbols in our system. So we often go to the letters to represent the other 9 or the other 10 possible digits. So A means 10, B means 11, and all the way up to J being 19. So the example I give here is 74DJ in base 20 would be 7 times 20 cubed, 4 times 20 squared, 13 times 20, plus 19 times 20 to the 0, which is 1, which ends up giving you this numeral right here in base 10, 57,879. And if you wanted to count up, it's pretty easy. You just up the last symbol. So J would become a 0. It'd wrap back around, and then D would become an E, right? So that's how we would do it with, Arabic numerals, but obviously the Maya didn't have that. So what were their digits? What symbols did they use? Well, in ceremonial or more formal representations, they use these head glyphs, which you can see there's some patterns here, right? They have unique words for everything from 0 up until 12. Kind of like we do in the English, right? 0 through 12, all unique words. But then once we get to 13, we start concatenating. 13, 14, 15. They did the same thing, actually. You can see that from their 13, ox lahan is lahan, meaning 10, ox, meaning 3. The same thing for 14, can lahan, olahan, and etc., right? So it's interesting how they follow the same sort of phonetic pattern that we do in English. But these head glyphs are not obviously great for doing arithmetic and math. So What they instead had were these three basic symbols. They had a shell, an empty turtle shell, meaning 0. They had a stick or a dot, meaning 1. And then they had a full stick, which means 5, pictured here below for reference. So they use stick, stones, and shells, so I had to call it. And so the 20 Maya digits actually are captured in this chart here. And you can see that counting from 0 to 19 is pretty straightforward, right? You just keep adding dots until you get to 5, and then you create a bar, and then you go on from there. So you can see the multiples of 5 just have bars on them. And then, you know, for every number mod 5, you just add more stones to it. So counting up from a given Mayan numeral is a bit different because you don't count horizontally from right to left like we do. You count vertically from bottom to top, but it's sort of the same algorithm as the way we would count. So here I show you just so that you can compare it to the algorithm for counting in Arabic, which is pretty much the same process, same number of steps. And here I have an example where we start from 0. So I've got Maya digits in the brown, decimals in the white column, and they had names for their place values, much like we do. Like we have tens, hundreds, thousands, 10,000s. They had unique names for their place values from 20 to the 0 up to, I think, about 20 to the 6th. So if you're going to count in Mayan numerals, that would be 1, 2, 3, 4, replace for 5, 6, 7, 8, 9, replace, 11, 12, 13, 14, 15, 16, 17, 18, 19, and then you would move up a place value. So that's 20. And then you put a 0 in the 1's place value, if you will. And then you can keep counting as you would. And eventually you'll get to something like 39, right? A 1, 20, and 19 ones. And then if you count up again, you get 40, right? 2 20s, 0 1s. And then eventually, if you keep doing this, you'll get 19 and 19, which calculates to 399. So then the 400, you'd have to move to the 400s place, right? So count you the same way that we count. We just use place base 20 instead of base 10. And then you can keep going, right? So how do we convert from Mayan numerals to decimals? Well, it's the same way that we convert Arabic numerals into what they mean, right? So here I would say that I have 4 400s, 13 20s, 2 1s, which calculates to 1862. As another example, if I had just a stick, a stone, and a shell, then that would be 5 400s, 1 20s, 0 1s, aka 2020, a year that will, of course, live in infamy. Then if we wanted to see what this number represented, we'd do the same thing. We have 6 160,000s. We have 5 8,000s. That adds up to a million. You can check my math there. So if you want to express what a millionaire looks like, this is how you do it in Maya digits. And then if I wanted to put 19s in all these place values, I could do the multiplication to figure this out, but I'd rather notice that this is just 1 less than the next place value. So 3,200,000 minus 1, that's how I get this number, right? So now let's talk about how do we do arithmetic with Mayan numerals. And addition is probably the first arithmetic operation we learn how to do with numbers. So let's start there. This is where I really get fascinated by the system, because to add Mayan numerals, there are really only 3 rules. You're going to combine the digits in the place value just horizontally and ignore any shells that you see. And starting from the lowest place value to the highest, there's just 2 rules that you have to apply. If ever you see 5 stones, replace it with a stick in the same exact cell. If ever you see 4 sticks, replace it with a dot in the cell above, right? So this translates into like sort of our like conversion when we have to go up to the next place value. And you just put an empty shell in any empty cells that are left over to hold the place value. So if you had to do 1 + 2 = 3 in Arabic numerals, you would have to either count up 2 times from 1, or have to memorize the fact that 1 + 2 = 3 if you're a child. But with Maya numerals, there's nothing to memorize, right? Adding is literally just putting the symbols together, kind of like an abacus. So that's how I'd add 1 + 2, right? There's no string of symbols to remember. It's just I concatenate them. If I had to add 2 + 2, again, this is actually a memorized fact, this equation up here. Whereas in Maya, I would just put 2 + 2 in my 2 cells here, and I'd get 4, right? You can see also, by the way, on the left, I have the place values, just not the names for the place values, just so that we can keep track of what each cell up in the column represents. So 3 plus 3 equals 6, same thing, except now I'd have 6 dots, and my rule says every time I see 5 dots, I turn it into a stick. And there I get the symbol for 6 again. If I do something more complicated, 9 plus 16, which is 25, again, I would have to do some weird carry stuff here. If I did 9 plus 6, I'd have to remember that that's 15, or I'd have to count up 6 times from 9. But here, if I have 9 plus 6, I just put them in my cells. I just literally move all the symbols over, just group them all together, and then apply my rules, right? 5 stones become a stick. 4 sticks become a stone in the cell above. So here I get literally 120 and 5 ones, 25. If I did something even more complicated, 64 plus 36 equals 100, again, I'd load in the symbols for those two numbers and just combine them horizontally in their place values. So I'd get something like this in the right column. And then I just apply the same conversion rules. 5 stones become a stick. 4 sticks become a stone up above. 5 stones here becomes another stone, becomes a stick here, and then I have an empty place, so I put a shell to hold the place value, and my addition is done, right? So a final example, let's go all the way. Let's take these two random large numbers and see how we'd add them together, just to see how efficient it is. So trust me, these are the Mayan numerals that represent these Arabic numerals. You can check my math if you want, but I'm just going to combine them horizontally. And then from bottom to top, just apply the conversion rules. So that becomes a stone above, 5 stones becomes a stick in this cell, 4 sticks become a stone above, 5 stones become a stick, 4 sticks become a stone above. 4 sticks here become another stone above, and then I just rewrite this. And I don't know what this is in Arabic, but nor do I care, right? This would have meaning to a Maya person, right? So I don't need to convert this. This is just the answer, right? So that's how I would add. And you can see I get a sense of the quantity of this just by the place values and how many I see in the highest place value. I can see that this is probably going to be something in the millions, since I'm taking literally 13 times 160,000, right? So how would you use subtraction? Well, subtraction works in a very similar way. There are also just 3 rules. The only difference is that now we have to do some borrowing, right? The way we would do in normal subtraction. So we're going to look at the smaller numeral cell and just take all the symbols we see and remove it, and do the same thing from the larger numeral cell. But sometimes we run out of symbols in the larger cell, so we have to do some converting either from the same cell or a cell above to be able to do the subtraction, which correlates to our borrowing from a higher place value. So to show an example of this, let's say I wanted to subtract these two numbers. I would load them in, put a subtraction in the middle, and then I can see in the bottom cell, I've got 3 stones and a stick. So I take away 3 stones and a stick from both of these, which gives me just that. Here I see an empty shell, which means nothing to take away, so I just remove it. And here I see 3 sticks and a stone, so I take 3 sticks and a stone from the larger number. And then this is just my result. End of story, right? So then there we have it. So again, if you think about this, the subtraction just revolves removing symbols, which is far more intuitive than saying, oh, well, let me take 3 minus 8. Oh, I can't do that. I've got to take 1 from the 5 and make that 13. And I still have to remember what 13 minus 8 is, right? Either by using my fingers or remembering that fact. If I do another example here, here I might have to do some converting. So in the lower place value, I have a shell at 0. I just remove it. Up above, I've got 2 stones, 2 sticks. I've got enough here, 2 stones, 2 sticks. I remove them. Here, I've got 4 stones, but I only have 2 stones here. So I'll remove whatever I can, which is a stone and 2 of these sticks. But I still have 2 stones left to remove, so I have to convert one of my sticks over here into 5 stones, like working backwards. So I do, and now my cup runneth over, right? I can now take away 2 stones, and I do, and that leaves me with just a stick plus 3 stones. I put a shell here for the place value holder, and this is my final answer, whatever this means, right? So that's the answer to the subtraction problem. And here we have another example. We've got 2 larger numbers to subtract, and here we're going to have to borrow. So I got 2 stones, or 3 stones, 2 sticks. I can take that away from the 1's value, leaving 1 stone. Here I've got 2 stones. I can take that away from here. Here I've got 3 sticks. Certainly don't have 3 sticks over here, so I'm going to have to take this 1 up above, this stone, convert it into 4 sticks below. So I take away what I can first, still have 2 sticks to deal with. So I convert that into 4 sticks, and now my cup runneth over once again, and I can take away these 2 sticks from both columns. And that leaves me with the final answer here. So that's the answer to that subtraction problem, essentially. And last but not least, if I take these 2 numbers and have to subtract them, first I load them up, and now you can see I'm going to have to do multiple borrows, because here I've got 3 sticks. I've got no sticks to speak of in here or here. So I'm going to have to start converting from the top place. So I take a stone from the top, and, well, first I take away the 3 stones that I can, right? Because I'm allowed to do that. But now I have to borrow a stone from the top. So if I do that, that gives me 4 sticks here. And then I still need something down here. So I convert one of these sticks to 5 stones. Then I have 5 stones. I have to convert one of them into 4 sticks below. So I do that, and now I should be all set. I take away my 3 sticks from each, which there we go. I take away my 3 sticks and 3 stones from here, from both places, and I take away 3 sticks, 3 stones from both places. And I'm just left with 25, which is the final answer. So again, it's really just about literally what subtraction means at its core, which is removing something from something else. So this feels more like the essence of subtracting 2 things from each other. As a last example of subtraction, I present these 2 numbers without giving you their Arabic translations, just to emphasize that there's one sort of difficulty here, which is how do you recognize if one number is actually greater than another? Here you can see that you'd get an error here, because these numbers from the top to the bottom are all the same until you get to the 20s place, where this actually has a higher 20 place value than this one. It's got an extra stone. So this would give you a negative number, and there's no evidence that the Maya even had negative numbers. So the Maya wouldn't ever do anything like this as far as we know. But it's really easy, then I'm sure we could define negative numbers and negative subtraction and Maya numerals. So this brings me to the next segment of the talk, which is how do we extend Maya mathematics to the kind of math that we would do? So first, think about multiplication, right? It's an operation we love to do. You probably had to remember this multiplication chart or your times table as a kid, and you might wonder, why did we go to 12? What a random number to go to for memorizing the times table. And, you know, I had to do these quizzes and remember what 9 times 7 is, right? And then we had this algorithm for doing 2-digit multiplication, which involves, you know, multiplying everything with everything in this weird way, and shifting over place values. But to multiply 2 Mayan numerals, there are really, again, only 3 rules, right? We're just going to multiply every symbol with every other symbol from the 2 numbers. That's what multiplication is. And we have these 3 multiplication rules. A shell times anything is a shell, kind of like 0 times anything is 0. A stone times anything is that thing, kind of like 1 times anything is anything. And then 2 sticks multiplied together gives you a stick and a stone above, right? It's like 5 times 5 is 25. This is all we need to do Maya multiplication. And the only thing that we have to keep in mind is that when we multiply 2 symbols, we multiply their place values as well. So we're going to put the result in whatever the product of the 2 place values is. And there's actually a nice geometric way to do this. But as an example, if I want to do 12 times 11, I load them in here, and then I highlight every pairing of symbols from the first and the second number. So here I multiply this stone by this entire thing. Remember, stone times anything gives you that thing. So I get that here. And I put it in the 1's place because I'm multiplying 2 things in the 1's place. Then I take the other stone times this whole thing. That gives me another copy of the whole thing. Then I take this stick times a stone, which is a stick. A stick times a stick is a stick and a stone above. A stick times a stick is another stick and a stone above, right? Then I do the last pairings. This stick times all of this. I can remember that the stick times the previous thing seemed to give me 3 sticks and 2 stones. So I can just shortcut and say this will give me 3 more sticks here, 2 more stones here. And then I just do my usual conversions, right? I convert things. I turn these into stones above. I turn 5 of these into a stick. and there's my answer, right? Another example, slightly more complicated this time. If I wanted to multiply these two numbers, now I've got 3 pairs of, or 9 pairs rather of things to multiply, but you'll still go faster than you might think. Here I've got 2 stones times this symbol for 6. So I'm just going to get 2 copies of that symbol. So there we go. Then I've got stick times stone, which is stick times stick, which is stick and a stone above. So then I can start shortcutting. A stick times this whole symbol gave me 2 sticks and 1 stone above. So these are the kinds of shortcuts you can remember if you're doing this quickly. And I get 2 sticks and a stone above. And then same for this multiplication. I would get 2 more sticks and a stone above, right? So I'm done multiplying these one place values. So then I start multiplying this pair. Well, you can start using your own, shortcuts. Like this is really 2 times 4, so it should give me 8. Or I can recognize that I should just have 2 copies of this symbol right here. But I should put it in the 20s place value because I'm taking 1s times 20s over here. So I get that. Then I do the stick times these 4, which should give me 4 sticks, 4 copies of the stick. So I get 4 copies of the stick. Same thing here. 4 more copies, 4 more copies. So then I start multiplying these 2, which should end up in the 400s place. So I have 1 times this symbol, so that should just give me that whole symbol up here, right? So now I move to the next place value. I'm multiplying this with everything over here. So now I've got the shell. The shell times all of these things, well, 0 times anything is 0. So this literally I can just skip. It means nothing. So I skip it. Then I go to this. Now I've got 2 copies of this symbol, but this should go in the 400s place because it's 400s times 1s. So I get 2 copies of this here. Then I've got 2 times these 4 dots. We've seen that that gives us 8 dots, but that should go in the 400s times 200s, the 8,000s place. And then I've got 2 times 1. Those are 400s times 400s. That should go in the top place value then. So I get 2 dots here. Then my multiplication is done. Now it's just converting. So I convert, I convert, I convert, I convert, I convert, I convert, and now I'm done converting. So this is my final answer. Now, I'm not going to discuss division, but I do want to talk about divisibility rules. And in particular, I want to compare them to the divisibility rules that we have for Hindu Arabic numerals, just to see what they're like, right? So dividing by 1, any number is divisible by 1. So that's easy. Dividing by 2, well, that's easy to tell in Hindu Arabic. You just look for a 0, 2, 4, 6, or 8 in the 1s place. But for Mayan numerals, you just look for an even number of objects or a shell in the 1s place. So you can discover what an even number is by just matching symbols, right? So for example, here, I can tell there's an even number of symbols here, not because I counted 1, 2, 3, 4, 5, 6, but I just match every stone with every stick. Hence, I have evenness here. So this must have been an even number without needing to convert this, right? By the way, you might notice in this tablet here, if you look very closely, you can spot a sequence of even numbers that whoever wrote this back in the day was contemplating. And if you haven't spotted it, it's this row right here. You can see that symbol for 2, 4, 6, that's 8. 2 stones is a 10, 12, 14, 16, 18. So you might wonder what other patterns are found in this codex, right? So interesting question. If I wanted divisibility rules for the number 3, in Arabic, you just add the digits and see if that's divisible by 3. In Mayan numerals, you take the alternating sum of the digits and see if that's divisible by 3. So for example, this number that I showed you before, in Arabic, I can tell it's divisible by 3 by adding the digits, and I get 33, clearly divisible by 3. But with Mayan numerals, I would take the alternating sum of these 5 digits here, which translates into this minus this plus this minus this plus that, which translates into this, which gives me 27, also divisible by 3. So that's how I would check divisibility. For divisibility by 4, all we really have to do is look at the last 2 digits in the numeral for Arabic and see if that's divisible by 4. But for Maya, it's kind of simpler. You just have, if you have 4 objects or a shell in the 1s place, you're divisible by 4. So here, this number, I'd have to then know if 76 is divisible by 4. Some people often struggle with this, like, can I divide that by 4? Can I not? Here, I just see that there are 4 things divisible by 4, right? I don't care what this represents. I know that this is divisible by 4. For divisibility by 5, I just check if there's a numeral in the 0, if there's a 0 or 5 in the ones place for Arabic. For Maya, just check that there's no stones in the ones place. Then it has to be divisible by 5, right? Like this number here, I see no stones, so I don't care even what this number is. It's automatically divisible by 5 because these place values are divisible by 5, right? For 6, just check divisibility by 2 and 3. That's the same in both systems. So here I can tell that this is divisible by 6 because it's divisible by both 2, even number of objects here, and divisible by 3. Alternating sum is divisible by 3. Divisible by 7, this margin is too narrow for Arabic numerals. There's a bit of a complicated rule for that. For Mayan numerals, there's actually a simpler rule. It's the same as the rule for 3. Take the alternating sum, check if it's divisible by 7. So here, this is an easy number to see this is divisible by 7, but in Mayan numerals, I would just take the alternating sum of these 3 digits. So this minus this plus that gives me 28 if you do the subtraction and addition and see this divisible by 7. For 8, you just check the number formed by the last 3 digits is divisible by 8. This can be really tricky, and the Maya rule is not much better. So here I put the text of it, but essentially you have to check 2 place values now in combination with each other. Basically, everything from the 400s higher is divisible by 8. So you have to check if the sum of these 2 is divisible by 8, which means if you have an even number of 20s and a certain number of symbols in here, then it's divisible by 8. So I can check that this one actually is divisible by 8. And the same with this number. I can check because I've got an odd number of 20s, an odd number of symbols, and I have a 4 in the ones place. So this must be divisible by 8. So not an easy rule to apply. Checking divisibility by 9 is really easy in Arabic. Just check if the sum of the digits is divisible by 9. The one from Maya is a bit too difficult, kind of like this one was for 7, so I won't go through it. But checking divisibility by 10 is really easy, right? Just check, do you have a 0 in the ones place? And here, you just check if you have a shell or 2 sticks in the ones place. So that's pretty easy rule. The rule for 19 in Arabic is, again, way too complicated. But the rule for 19 is actually really simple. Just like the rule for 9 in Arabic, just check if the sum of the digits is divisible by 19. So as an example, I would have a nightmare checking if this number in Arabic is divisible by 19. But if I translate it to Maya, just add up all those digits. We know how to do that now. And I get literally the symbol for 19. So whatever this is has to be divisible by 19, right? And in fact, that's 19 times 59,433 in case you are curious. So the rule for 20 is, of course, easy in both systems, right? For Hindu Arabic. Just check if the number formed by the last 2 digits is divisible by 20. And here, you just check if there's a shell in the ones place. So pretty easy. And so comparatively, you can see that for all of these divisors, there are sort of 2 rules in Arabic that you wouldn't want to check divisibility for. Whereas in Maya, there's really only one, which makes sense. We're using a higher base, so our numbers, there's more allowability for easy divisibility rules for that reason. How would you represent fractions and non-integer quantities with Maya numerals? Well, for example, 365.25 can be represented in Maya. We just have to extend our system a bit by converting this number, which is in base 10, including the 2 and the 5 after the decimal point, and doing some arithmetic to convert this into base 20 numbers. And we can do that. I won't show you how I came up with the base 20 representation, but I can see that it really is just 18, 5, and then 5 times 20 to the negative 1. So I can represent these negative place values by just putting a line here, and then going below. So the same way that we extend decimals off to the right. So this could be how I represent 365.25, right? 18 20s, 5 1s, and 5 20ths, if you will. I can do the same thing with 1/3. 1/3 translates into this infinite sum of fractions, which translates, believe me, into this infinite sort of double geometric sum of fractions, which is just 613, 613 repeating. So I have an infinite decimal here, which I can express as putting a 0 in the ones place, and then I got 6, 13, 6, 13 ad infinitum, right? So this is something that we can do. What about irrational numbers like pi? Well, 3.14159, so on, so on. Well, again, I can take this decimal expansion as a base of 10 powers of 10, And then I can still rewrite this in base 20. Again, don't ask me how I got these numerators, just trust me that those are the right numerators. And that would give me an infinite sum of fractions that have no pattern, but I can still calculate them all. So these would be my digits, 3, 2, 16, 12, 14, 16, so on. And again, I have my pi value in Maya. So if we ever saw a chart like this or found this in a codex somewhere, we might say that, well, maybe the Maya had some knowledge of trigonometry or circle geometry. And E, you can do the same thing. This is how you would express E in Maya numerals. So instead of 2.71828, you would have these digits here, random infinite pattern. If we ever found something like this, we'd go crazy because maybe that means that the Maya actually knew calculus. The truth is we'd never know the extent of what the Maya actually did accomplish because a lot of their work was destroyed, as I'll mention in a moment. So we don't know what mathematics they did or did not use besides just addition and subtraction. So how would I rate this system? So you might be surprised, but I actually give this system a perfect 10 rating in every category. And what I think it makes up for that the Arabic system lacks, particularly, is that there's only 3 symbols that are used, right? So the efficiency of symbols is miraculous, right? The efficiency of doing arithmetic and algebra is not only equally efficient, if not more efficient, as Arabic numerals, but it requires less memorization and it requires more intuitive understanding of what the operations are actually doing with numerals. I think it's even easier to express large numbers because you have a higher base, which means I can express large quantities really easily, which is why they're able to calculate their calendar hundreds and thousands of years into the future from where they lived. And you can see they're pretty easy to read and write because the Mayas were clever. They decided that using stones to count up single digits was easier to read through than using like the tally marks. Distinguishing between 3 and 4 was a difficult task. Here, it's not so much. It's really easy to distinguish between 3 and 4. And then once you get to 5, we don't want to keep using stones anymore because it's hard to read. So they smartly converted it to a single stick. So I think there's a lot to be learned about the efficiency of the system. And if you don't trust that, you can trust these articles here. There have been many articles studying the effects of different school systems introducing Maya mathematics to kids at an early age. And you can see that they have had a large impact on student learning. And this was largely due to this one professor in Mexico who discovered an ancient book from a Spanish missionary who actually went to the Maya civilization, compiled all the things that he learned from them in this account, and then burned documents that he didn't like, which is why we have a lot of lost records of the Maya, systems. But he came across this book in the 70s, introduced it to his students in Toronto, and found that they really loved it and they took to math more easily. So he went to international conferences, he shared the system, and then in Spain, he met a colleague who had a daughter with learning disabilities and shared his system with the colleague. The colleague shared it with his daughter, and the daughter was excelling in mathematics for the first time in her life. And so he decided, what if I teach this to the students, for whom this would benefit the most, namely the indigenous Maya people? So he did a few experiments and trained teachers how to do this system in the schools. And within 2 years, these indigenous students who are the lowest performing in the country ended up becoming some of the highest performing math students in Mexico, even compared to private school students. So there really is a lot of research so that there's a big efficacy to the system and that we should learn something from it. And here are just a few clippings of articles that talk about like the growth in student achievement because of the Maya system here. The last thing I want to just briefly touch on, because I know we're short on time, is just a few other numeral systems that I wanted to highlight because there's something to be said and learned about them. Of course, we heard of the Babylonian system, which was base 60. So they literally had 59 different symbols. I don't think they had a symbol for 0. But just with these base 60 numbers, they were able to do incredible mathematics, such as also approximate rational and real numbers. Then you've got the duodecimal system, which I find is really interesting because a lot of cultures actually use base 12 systems. And it's the reason why 12 is so prevalent in so many elements of our civilization, all the way to multiplication tables, a dozen eggs. The old English customary system relied heavily on base 12 numbers. And there's actually been lots of mathematicians and, in fact, societies like the Docile Society of Great Britain, which I think still exists, which highly advocate for using base 12 instead of base 10. I like this quote here that someone came to the conclusion that the decimal system should be rated about 65 or less if we assign 100 to the duodecimal system. So also a system worth checking out. Also, you can see here that the symbol for their society is actually a circle of fifths. If any of you are musicians, you know there are 12 notes that we write music in. But last but not least, my favorite system of all has to be the Kaktovik or Alaskan numeral system. And why is it my favorite? Because it's also a base 20 system, like the Mayas. Most systems that originate in the Americas actually are base 20, which is an interesting connection. But what's cool about this is that it wasn't discovered by mathematicians or founded by a society of people. Rather, it was invented by middle school students. I mean, literally middle school students decided that Arabic numerals were too hard for them to learn. And so they created their own with these ideas in mind, very similar to the ideals that I have. And they created this system of 20 numbers, which are really visually easy to write, read, and remember. And you can see here that they just use single strokes to indicate numbers like tally marks, but they go in different directions. And they use this upstroke here on the tops of their numbers to indicate moving to higher values. And then they also concatenate to make place values. And here there's an example of division. I won't go through it, but this example is fascinating because this is a long division example where if you had to do this in Arabic numerals, it would be a nightmare. But because of the way they invented their symbols, division is actually visually represented. So they could do this division of 5, 6 decimal place numbers literally with a couple of strokes because they invented their system that way with the help of their teacher. And this system was, again, so effective that their teacher went to a conference at the Board of Education in Alaska and spread it throughout all of indigenous Alaskan schools. You can see some pictures here of kids using these toys and symbols to, solve math problems. And again, they saw huge gains in the math skills of these students across the board. And for example, the California Achievement Test. So there's a lot of research to show that introducing all of these different numeral systems to students early on has a major impact on their ability to cognitively understand what numbers actually are. So this is what I'll leave you with. And here are some of my sources. If you want to leave them, we can always send you my slides as well if you're curious. But I believe that's all I've got. So thank you all very much.
Thank you, Akeem, for this very interesting and fun talk. Or we gave a round of applause over here. Can we use your laptop for like a couple of minutes longer? Okay. So I realized like a couple of people have left because there is another talk. But if there are any questions, I think Akeem would be happy to answer those.
I see a hand, I think.
I see a hand.
Yeah, I'll speak loudly, so hopefully you can hear me. Just from your sort of conclusions in the school section, you've sort of been saying that the evidence with these different systems of children excelling. Do you think the worldwide use of the Arabic system is leading to limitations in children's mathematics then?
Did you say limitations in doing mathematics?
Yeah, do you think the fact that we rely on base 10 leads to limitations in young children that the use of these base 20 systems seem to eliminate?
Again, and I wouldn't say I'm an expert in, math education research or anything like that, but my opinion, just based on what I've read, is that it's not so much relying on particularly our Arabic base 10 numeral system, but the fact that we typically only teach one numeral system, I think is really the issue. I think if students from an early age learn not to just associate the idea of a number to one set of numerals, but rather to really see numbers for what they are, I think that's what we should be doing. Because, again, my biggest gripe with the Arabic system is that the symbols are very arbitrary. Like, besides the symbol for 1, which is a single stroke, pretty much derived from tally marks, 2, 3, 4, etc. What connection do they have to the actual number that they represent in our mind, right? Symbols like the Alaskan one, the Mayan one, and other ones across other cultures have a more direct connection to what we think of when we think of the number 4 or the number 7. And that's something that I think is you know, necessary for little students in math to be able to, you know, connect mathematical ideas easily, especially ideas of like numeracy and how to do operations. So I think there's nothing wrong, particularly with learning the base 10 system, but the fact that we only teach base 10, it's almost as if we're enforcing this idea that mathematics is arbitrary and that it's not actually connected to the world and the universe we're studying. So that's really my gripe with it. And I feel like if we taught systems that were more visually representative of numbers, then, you know, we'd have a more complete understanding of what number manipulation means, and possibly down the road, how do we really do number theory, you know, because number theory is really all about studying not just any particular system of numbers, but how the ideas of numbers interact with each other. So if kids learn that early on, I think that that'd be a huge advantage.
Thanks, that's such an interesting thought experiment, really, yeah.
Yeah, it's the kind of thing where I wish I knew more growing up.
Yeah.
Are there any other questions? If not, I have like one small question, because at the start you showed us the hats that they were using, like as a more formal system. Is there any way that the sticks and the stones and the shells are like occurring in those pictograms as well, or is it just their way of like having a formal number for it as well?
No, I don't think there was any connection. In fact, the head glyphs were rarely used. They were used sort of more in describing like certain religious doctrine, and you rarely see them in the Dresden Codex, for example. Almost never, in fact. You see rows and rows of the, you know, stick, stone, shells, because I think that's what they commonly use their numbers for arithmetic, like that they were counting crop yields and, you know, solar days and things like that. So they really did need a system that was not just good for counting, but good for, you know, arithmetic. And they quickly knew that the head glyphs were not good for that. So, you know, you see, so I think it speaks to like what they thought numbers were used for, as opposed to like tally marks or Roman numerals. They wanted their numbers to really have arithmetic meaning. So yeah, there's no real connection. I think the article I read said that the sticks, stones, and shells were used by more the common people, like to just do calculations like in marketplaces. But the head glyphs were more just like recording official documents that were, you know, meant to be passed on.
Okay, interesting. Then, if there are no other questions, let's give another round of applause. Thank you very much, Hakeem. It was a very interesting talk.
Thank you, folks.
I'll see if I can stop sharing. Oh, great. Cool. Remind me of your name again.